thank you very much for inviting me. It's a big honor to be here. Please, do interrupt me and ask me questions. So I think this is, we have a little bit more time than I would have in my home institution, so we can use that to actually help you understand stuff. Okay? So, the connection between topology and dynamical systems goes back to Poincaré. So here, dynamical systems is sort of the simplest case. Let's say we have some map, and we iterate that map. We do it over and over. And so Poincaré thought, well, what we should do first is we should understand the fixed points, the points that are fixed, and the points that are periodic, that come back to themselves after finitely many times. And then after we understand those, we could look what happens for points which are very close to one of the periodic points. And like that, we would work ourselves up to a complete topological understanding of the map. So what happened is that the topologists sort of only got the beginning of the message. So we are still stuck with fixed points and periodic points, and have not been very successful with the rest of the dynamics, at least as far as topology is concerned. But that is what happens. So I am actually not an expert in these kinds of things. The question is, why am I actually giving a lecture about it? And the answer to that is, I wish you wouldn't ask me that. But there have been some recent developments, very recent, that I think it's interesting to talk about. Okay, and sort of brought up new interest in this question. So, so this lecture is about iterations of maps in Hamiltonian dynamics, so in symplectic geometry. So let me start with the simplest kind of maps, which is linear maps. Okay? So there is a lot on each. This is my patented method for slides. It combines the disadvantages of a board talk. So what I want to look at is it's an element of the linear symplectic group. Okay, so the linear symplectic group is linear maps of R2n, which are compatible with this symplectic structure that I wrote in P and Q coordinates, as in classical mechanics. Or if you like, okay, they are linear invertible linear maps which satisfy this equation here. Oopsie, there you go. Okay. Yeah, this is a little clumsy. What I did is I wrote this form here in terms of two pieces. One is the standard linear product, and one is the complex structure, where I think of R2n as being C to the n. Really, they only have to preserve the combination of those two. So that makes them symplectic linear maps. All of them have determinant 1. And so if you did the linear algebra of these, they would teach you that the eigenvalues come in certain eigenvalue configurations. So one of the things is there could be a real eigenvalue lambda and a real eigenvalue lambda inverse. So in one direction gets stretched, and the other, the p direction gets stretched, and the corresponding q direction gets compressed. That is a symplectic linear map. The other thing is rotations in 2 dimensions are also symplectic linear maps. So there's two eigenvalues that come on the unit circle and are complex conjugates. And there is a third configuration where you have 4 non-real eigenvalues, so mu and mu bar, and then mu bar inverse and mu inverse. And already from what I told you, you can see that the determinant is 1. Okay? So what I'm interested in is, so because of this form here, for instance, you have only R2, you have dp wedge dq. So the R2 is oriented. So when you have a rotation, there is an intrinsic difference between forward and backward rotation. So I'm interested in sort of something like the amount of rotation. So I think of this one here as having amount of rotation 0. Okay? And this one here has amount of rotation, which is more or less the angle. And this one here again as having amount of rotation 0. Now, here there's an ambiguity between theta and theta plus or minus 2 pi. So to resolve that ambiguity, I will work not with this Lie group here as P2n, but with its universal cover. Okay? So the universal cover is, so if you look at, for instance, you could look at the maximal complex subgroup. So the same thing is the orthogonal group. So these are now things that preserve the symplectic structure and the inner product, and therefore they also preserve this complex structure. So the maximal complex subgroup is the unitary group, and then the fundamental group of the unitary group is the infinite cyclic, and that's it's also the fundamental group of the linear symplectic group. So the universal cover SP tilde to n is an infinite cyclic cover, and it restricts to the infinite cyclic cover of the unitary group. So So that basically means if I lift something to the infinite cover, then I am actually choosing a real value of theta, so that the amount of rotation makes sense. So the outcome of this is something called the rotation number. Okay? It's not quite as straightforward as it has maybe made up here. So on UN you have the complex determinant, which goes into the unit circle in C. Okay? If you take the universal cover of this, there's a lift to the determinant, which is real value. There's some slightly funny conventions for how I think of R as the universal cover of S1 here. But in case you wonder what signs, let's refer to those. And then you can actually extend this to a map from the universal cover of the linear symplectic group to R, but that is no longer a homomorphism of groups. Okay, this is called the rotation number. At least for n equals 1, it actually also goes back to Poincaré. So what it is it's what's called a homogeneous quasimorphism. So homogeneous means if you take, so I put A tilde if I want to choose a lift of A to the universal cover, and if you take the kth iterate of this, then the rotation number gets multiplied by k. And it's not quite a homomorphism, so if the homomorphism this would be 0. But it is a quasimorphism, means there's a universal constant, 2n or something, maybe n, such that the difference between those two things, so that the failure of it to be a homomorphism, is bounded. Okay? And if you have just the rotation, then it really gives you the real angle of rotation, what you think of. Okay, so this is, so basically it's constructed in the way that I said here, is you focus on the rotations and you throw away everything else. The problem with that picture is that you're proving that it's a quasimorphism.
That's supposed to be a sum, right?
What's supposed to be a sum? Oh, I'm sorry, plus, yes. Sorry. You should add real numbers and not multiply them. Apologies. Okay, so obviously, when you study, what I mean by studying iterations, you take powers of the, so the key thing is that, we have this homogeneous quasimorphism, which is the rotation number, and that tells you which way you're roughly going. Now, for reasons which are not obvious, I want to look at something which is a slight variant of this rotation number, which has an advantage of being an integer. So what happens is, let's first look at this one here. So SP2 and star, this is an open dense subset. These are all those such that 1 is not an eigenvalue. Okay, so there is no invariant vector. So in that case, obviously 1 minus A is invertible. And you can look at its determinant here, and it's either positive or negative, and you look at its sign. So this gives you a map from this open subset, which is not a group, to plus or minus 1. Okay? In fact, this subset here has 2 connected components, and this separates the 2 connected components. And if you're familiar with the Lefschetz fixed point theorem, you see why I'm doing this. And what happens is, so far I could have just put GL, but for symplectic matrices there's something slightly better. If I look at the pre-image of this SP2 and star, what I could call them non-degenerate matrices, in the universal cover, and I denote it by this, then there's a lift of that map to integers, which means there's an integer you can associate to this, which is either even or odd, depending on the previous sign here. Okay? This is called the Colli-Zehnder index. It's not defined on the whole of FP tilde, but it has a big advantage of being an integer. Roughly speaking, you can think of it like this: because I'm on the universal cover, I can choose a path homotopically uniquely from the identity to my A tilde. A tilde does not have 1 as an eigenvalue, but somewhere in the middle along this path, I may cross the eigenvalue. The eigenvalues may cross 1, and they may cross it in various ways, and it counts the crossing with signs. Okay? So this is the Colli-Zehnder index. So for instance, if you take this matrix here, so this is sort of expanding one direction, contracting the other, there's some normalization issues. So the Colli-Zehnder index for me is always 1. So another thing, so the linear algebra, so the Lie algebra of the linear symplectic group can be identified with symmetric matrices, like this. So I take a symmetric matrix, and this will be the exponential is a group element. And in this case here, if you exponentiate with it for small positive time, then this Colli-Zehnder index gives you the Morse index of the symmetric matrix, which is the number of negative eigenvalues. And let me show you slightly more it's an important example. So this is a rotation matrix. So if you start with a rotation matrix, say theta is positive and small, the commutator index is 0, and then when you rotate, and you rotate once around, and you come back, once you cross 2 pi, the commutator index will go down by 2, and become -2, and if you cross again, it will become -4, and then -6. So, okay. And also there's some symmetry, you know, if you pass to the inverse. So the relation between the two is actually that this commutator index, the problem with this mu is it's not homogeneous with respect to taking powers. Okay? In fact, you know, there's whole books written about the relationship between mu of A and mu of A to the K. They're not very interesting, but what we can do is actually the two things are roughly speaking the same as in the sort of quasimorphism sense, which means the commutator index, you can take the rotation number and you can add a correction which is strictly in between 0 and 2n, and that will be, so it's a way of essentially taking the rotation number and making a bounded correction which makes it an integer. Okay? We good? So let me give you an extremely stupid application, okay? To this simple, so it's the simplest possible statement. So what happens, I take a tilde and I take all its powers and assume that they're all, you know, one never becomes an eigenvalue, so the commutator indices are always defined, and I ask myself, what happens to this thing here, okay? So well, either it goes to plus infinity, as k goes to infinity, or it goes to minus infinity, or it forever stays strictly in between 0 and 2n. And that's simply because if the rotation number is positive, then as you iterate, there'll be a multiple of the same rotation number, and that will predominate this arrow. It'll often go to plus infinity. If it's negative, it'll often go to minus infinity. If you are here, then, well, sorry. So if the rotation number is positive, we go there. If the rotation number is negative, we go there. If the rotation number is 0, then you're always, for all iterates, the rotation number is 0, and you'll always stay in between 0 and 2n. Okay, so that's the simplest iteration statement. Obviously, for this thing, you don't actually have to write a book. The books are all about, you know, the finer details of this asymptotic behavior. But this is as much as I want to say about linear algebra. Okay? You happy with the linear algebra? Okay. So now I pass to the sort of nonlinear iteration. Okay? So this comes from classical mechanics, in a, you know, by some fairly complicated route. So in classical mechanics, you know, if you give you the dynamics, you need a Hamiltonian. Okay, the Hamiltonian defines the evolution of your system. Here I want to assume that my Hamiltonian is a function of P and Q. Let's say at the moment it could be in R to N, and I'm going to assume that the function is time dependent, so it's not autonomous. Okay, and then it gives you an ordinary differential equation, which are the Hamiltonian equations of motion. dP by dt and dq by dt are the derivatives of this function here. So for instance, if you take, you know, sort of classical mechanics, you took you know, the kinetic energy, and there's a potential energy here, then you would get the equation. So P dot is minus dH by dq, so it's minus the gradient of this one here. Q dot is the gradient of this, which is P, and you combine them all, and you get Newton's equation of motion, right? The Q double dot is minus the gradient of the potential. What I want to do here, which I'm not going to further motivate, but is I'm going to assume that my time dependence is periodic. So you have like a mechanical system which is stimulated, which changes, but changes in a time periodic way. And then it makes sense to look for trajectories of your system which come back to themselves after time 1 or time 2 or time 3 and so on. And it wouldn't make sense to look for trajectories which come back to themselves after time, you know, 1 over square root of 2, because those equations are not actually consistent. There can be no such trajectories. Okay? So this is what I'm going to look at. So this makes it look like discrete iteration, in fact what it is. So globally, so if we don't work with R2N, we can find any, I can choose any manifold, and I want to choose something that's compact and without boundary. And I need a replacement of this, you know, here there's something happening with the P and Q coordinates, which is given by a symplectic form. So the symplectic form is a closed 2 form. Okay, closed real 2 form on your manifold. Well, it's actually around each point there are coordinates, and it just looks like this standard constant symplectic structure. And then if I give you a function that you take the derivative of the function, it interacts with the symplectic form, it gives you a vector field x, which is called the Hamiltonian vector field of this function. And I can write down the equations of motion, which are these equations here. That's the version of that equation. So what I want to assume is, again, that the function is t-dependent, and I get a t-dependent vector field. And I evolve this, and I get a family of diffeomorphisms of the dynamical. It's not a flow because the vector field is time-dependent. Now, as before, I'm going to assume that the function is one periodic in time, and then, it's not a flow, but if you change the time by integer, it's given by, so you have the time 1 map, phi 1. And if you want to know what phi t plus 2 is, you can take phi t and compose it with the second iterate of the time 1 map. So the important thing for the long-term behavior of the system is this time 1 map here, which I just called phi. Okay? And then the k periodic trajectories just become the k periodic points of this phi. So I'm always going to look at maps phi that are obtained in this way from a time-dependent Hamiltonian function. And now I'm asking myself, what are the fixed points? What are the periodic points? What can I say based on topological considerations? Okay? Now, because I'm a topologist, so there's two points about this fixed point and periodic thing. The global structure, like how does it depend on the topology of the vector, and the local structure, what happens near each fixed point. Okay? Because I'm a topologist, I want the local question to be as simple as possible. Okay? So I'm going to impose some kind of non-degenerate assumptions. If it was a fixed point, I would say, yes, I don't want one. So in the 19th century, they would have said, I don't want to have any infinitely close fixed points to mine. Here I would say, I don't want one to be an eigenvalue of the derivative of that fixed point, which also means that this actual derivative will be an element of SP2 and star, this subset that I defined before. Okay, one not an eigenvalue. Or you can also say, if I want to look at periodic points, and that's what I'm going to look at mostly, I want to make sure that not only is one not an eigenvalue of the derivative of this, but that's the same thing for all the iterates, which means that I'm assuming that there's no root of unity is an eigenvalue. So not only, so if it's a periodic point, it's a fixed point of phi k, or of phi 2k, and so on, they are all non-degenerate. Okay? And I could say, well, generically this is satisfied. Generically, this is, all the periodic points are non-degenerate, which means after a small perturbation of the Hamiltonian. Okay? Now, to be totally honest, if you're a dynamical systems person, you would say, you are crazy man, because we're looking for periodic points of some unknown system. How can you make a non-degeneracy assumption about something that you don't actually know anything about? And I think that's correct, it's correct. But in practice, when you study these things, things often boil down into two parts. The global consideration and then local arguments, if you have degenerate fixed points. So I don't want to talk about the local arguments at all, which can be quite complicated. So I'm always making this non-degeneracy assumption. It's easier for me. That's a point. So first question would be, so how many fixed points does it have? Okay? And about that, we actually know a lot. Okay? So the simplest case would be the case where you have a time-dependent, time-independent Hamiltonian. Okay? So an autonomous system. And if you look at just the local coordinate version, you'll see that if you have a point that's a critical point, so dh by dq and dh by dp all are all 0, then there's a stationary solution of your Hamiltonian equation. So that point is always a fixed point, if you have a critical. And if you make your function really small, and you assume that the critical points are non-degenerate, so it's a Morse function, then these are all the fixed points. So the fixed points in that case would just correspond to critical points, which we know a lot about because we have Morse theory. So, one of the, now a theorem, but a foundational problem in symplectic topology was the Arnold conjecture, which said, this is true, we can do kind of Morse theory, not just for time independent, but for time dependent. So now going back to the general case. Okay? So phi is a time 1 map of some time dependent Hamiltonian. And if you assume that the fixed points are non-degenerate, the number of fixed points is greater or equal than the total dimension of the cohomology of your manifolds, with some coefficient. To say coefficients in some field. Okay? So this is foundational, and this was proved. This is a long story. With rational coefficients, so f is a field of characteristic 0, let's say, it was proved around 2000 by various teams of people. The positive characteristic case is very complicated, and in general, for general M, was proved only this year by Abusite and Bloomberg. So anyway, so we have a lower bound. So this thing here with the Morse function, that was just motivation. Okay? It's known that if you have a Morse function, it has to have at least as many critical points as this thing here. Those are the Morse inequalities. But that actually extends to the general sort of Hamiltonian case. So the number of case points. Okay, but that's not what I'm interested in. I'm interested in periodic point situation. Okay? Okay, so there we go. Okay. So now, phi is this Hamiltonian map, and I'm assuming it's not generate periodic points. So the question, so let's go by the name of conic conjectures, in only general case of conic conjecture is this, are there necessarily infinitely many periodic points? Okay? So if I iterate and I look at periodic points of all periods, are there infinitely many? This is a very simple conjecture to resolve because the answer is no. Okay? So if you take S2, you can take phi, make a Hamiltonian function that has a maximum here and a minimum there, and so the phi could be sort of an irrational. Just h is just a z coordinate. Then phi will be a rotation, and if you scale it so that it's an irrational rotation, then so rotation with irrational angle, then no matter how you iterate, there are no other periodic points other than the south pole and the north pole, meaning 2. And the same thing is true, so if you have a manifold which carries a torus action, such that the fixed points, there are finitely many fixed points for the torus action, then you can choose some irrational direction in the torus and go there. And so in that sense, the answer is always no. Okay, fine. But in other cases, it's actually yes. The first case, at least in higher dimensions, which is what I'm interested in, was for the standard torus. So you take R2n, excuse me, typo, divided by its integer lattice with the standard constant symplectic form. And then there are always infinitely many periodic points. And that was proved by Collier and Seidel in 1984. Okay, so the question is, what does the torus have, what does the sphere have that the torus does not have, and vice versa? Okay? These are just 2 examples. Okay, so then...
Excuse me?
Yes?
Couldn't you just move this
yes.
to an irrational number?
I love your question, okay? So the question was, if I have the torus, can't I just take the translation by constant irrational amount? It never has any periodic points. Yeah, you can, but this is not Hamiltonian. So if you take something from a Hamiltonian function, you will always get something such that the average amount of translation is 0. Something that's called a flux. Okay? So this is not Hamiltonian. Okay, so it's important that the function phi be obtained from a time-dependent Hamiltonian. Okay. Even though these translations are symplectic, they preserve the symplectic map, but they're not Hamiltonian. So, okay. So the question, so we look at the topology of these and we try to figure out what the difference is. So there are there are certain basic cohomology classes that every symplectic manifold has. So the symplectic form is a closed 2 form, so it gives you a cohomology class in real cohomology. Also, a symplectic manifold is a manifold whose terminant number has a structure group that's the symplectic linear group. Okay. Or you could also say, from a homotopy point of view, the structure group is the unitary group because it's the maximum common set. So a symplectic manifold has Chern classes. Okay. And the one that's simplest one, the first Chern class, is an integer class in the second cohomology. And now you see, well, there's some different here, which is the first Chern class of M is of the torus is 0, and the first Chern class of the 2 sphere is definitely not 0. Okay? Ah, good. And indeed, so then there was a whole slew of progress over the years about the conic conjecture using various topological features. Okay? So first, the proof from the torus was generalized to any symplectic manifold where the first Chern class is 0 by Zabrodsky and Seidel in 1992. And things start getting slightly more strange. Okay? So the question so is also yes. Okay? So there are always infinitely many periodic points if the first Chern class is minus the cohomology class of the symplectic form. Okay, that's proved by Gibson 2010. So for S2, it's the opposite is true. The first Chern class is plus the cohomology class of the symplectic form. So this sign is going to push. I'm not going to go through the whole history. There's a whole bunch of other things which all have sort of topological assumptions and say yes if this is topology system. But from my point of view, topology cannot really be enough. Okay, and my pet problem is this one here. There are certain symplectic form manifolds. It's best to explain them from algebraic geometry. So take CP2 and take 1, 2, 3, 4, up to 8 points and blow them up. Okay? So that gives you what's called the tensor surface. So I want to take the first term, in that case I can take the first term as equal to the cohomology class of the symplectic form in algebraic geometry by choosing a suitable scalar form, and that's why you can only go up to 8 points. Okay? So this gets more and more complicated. You start with CP2, go up 1, 2, 3, 4, 5. But topologically speaking, they're all very similar. They all satisfy this one here. And algebrageometrically, they're all very similar. Okay? But since we know quite a lot about the symplectic topology, we know that the symplectic topology shows some kind of transition. Okay? So, first of all, if you blow up at most 3 points, then you can choose the 3 points to be fixed points of the torus action on CP2. And this will carry a torus action with isolated fixed points. And so, if you blow up less or equal than 3 fixed points, the answer to the conic conjecture is no for the same reason as here. Okay? So it means torus action, you can make sometimes finite dimensional. From 4 onwards, we have no idea. Okay? So what happens is we know a lot about the symplectic topology of these things. The symplectic topology does a big change at 5. Okay? I cannot really explain this to you in a clear way, but the simplest way to think about it is if you think about algebraic geometry. Okay? So when you choose 4 generic points on CP2, there are no moduli. Any 4 points on CP2 can be mapped to any other 4 points on CP2 if they're generic by a linear projective transformation. But from 5 onwards, you have moduli. Okay? And the moduli spaces are quite complicated spaces. They get more and more complicated as things increase. And so that actually influences the symplectic topology of these 4 manifolds. And so we kind of expect things to change, but we have no idea. Okay, so the conic conjecture is completely open. And topological methods aren't going to help you because from a topology point of view, there's really no big difference between blowing up 3, 4, or 5 points. Okay? Good. All right. So what's my next plan? So this is already reached the border of our ignorance, but it's interesting, right? Okay, so now I will, my next task is to give you enough, so I want to explain to you the proof of the conic conjecture for C1 equals to 0, okay, which is also a good introduction to the method of modern symplectic topology in general. And, okay, there's some technical stuff, but it's remarkably simple. Okay, but I need one thing, which is called Flow homology. Okay. So Flow homology is a kind of infinite dimensional Morse theory, which is based on the fact, which is very well known for classical mechanics, that solutions of classical equations of motions are solutions of a variational principle. They are critical points of an appropriate function, the Hamilton-Jacobi action function. So in a modern formulation where I'm looking at this map phi here instead of the Hamiltonian function, which I could also do, it looks like this. I'm going to look at a space which is like a free loop space of your manifold, but twisted. So there are maps from R to N, such that if I go from T to T plus 1, I don't come back to itself, but I come back to itself up to phi. Okay? So the best way to think about it is you start at 0 and 1, and then when you get to 1, if you do apply phi, you get back to x of 0. That's called a phi twisted loop space. And so this space carries an action functional, which is unfortunately not single valued, it has periods, so I can't mention A of x. I can't really very easily write down for you what A of x is, but I can write down for you what dA of x is. Okay? So dA is the differential of this. So I take a point x in my loop space, which is this loop, and I take a vector field along the loop, which is a deformation of the loop, and then dA of x in direction of psi is very simple. You have 2 kinds of things to do. You have psi, which is this vector field, and you have another vector field around this, which is just the derivative, x prime dx by dt. You stick both of them into this 2 form, you get a number integrate from 0 to 1. Okay? That's the derivative. So in particular, what does it mean to have a critical point here? A critical point means this is 0 no matter what psi you put in. So this one has to be 0 no matter what psi you put in, which unfortunately means that, well, it means that x prime has to be 0. So x has to be constant. But constant, remember, it's a constant map, it also has to satisfy this periodicity condition. So it has to be constant at a fixed point of phi. So the critical points of this are just fixed points of phi. Okay? And if you ask yourself, well, what is this weird non-degeneracy condition on the fixed points that I impose? It's the same thing as a formal thing of saying that this is a Morse function. The second derivative is non-degenerate. which you want. Okay? So Moore's theory, one way to define Moore's theory for a function is that you say I build a complex which has one chain complex, which has one generator for each critical point, and that gives you a complex computes the cohomology of the manifold. Okay? So here we're not going to compute the cohomology of this thing here because we have infinite dimensions and things are slightly strange. But we do the same thing. So we build a chain complex that has one generator for each fixed point. You have to choose just ordinary cohomology, you have to choose some coefficients. Let's say for my just take coefficients on field. Let's say for a moment like the rationals or something, field of characteristics. So you take this has one generator for each fixed point, and there's a differential which is kind of complicated to define, and the cohomology of this chain complex will define something which is called the Floer cohomology of phi. And, well, surprisingly, the Floer cohomology of phi has nothing to do with the topology of this space here. Instead, actually, it computes the ordinary cohomology of the manifold, independent, irrelevant of whatever phi is. Well, one way to say this is, suppose that phi was the identity, which of course has degenerate fixed point, then all the critical locus consists of constant solutions, like one copy of M for constant solutions. So it makes sense to compute the cohomology of M, and then it's kind of invariant to an area phi. Okay? So there's a canonical isomorphism with the ordinary cohomology. And the Arnold conjecture, which was this lower bound here, follows immediately from that. Right? Because I say you build a chain complex out of fixed points, and its cohomology computes the cohomology of the manifold. So you need at least as many generators in your complex as the rank of the cohomology. Okay? So this is essentially the Arnold conjecture is nowadays you would say, oh, what he was trying to say is Floer cohomology exists. Okay? Okay, so this is the Floer cohomology here. Okay, now I have to I lied to you in so many ways. Okay? So one of the ways that I lied to you is the question of what is the grading in this chain complex? Okay? So this should be, so to every x I should assign an integer. Okay, generally speaking, that's impossible. Okay, there's only a Z12 grading, but if you assume that the first Chern class is 0, okay, this is why you prove the Common conjecture that is, then every fixed point can be associated with an integer. And the way that you do it is you take d phi x, which is an element of the linear symplectic group, the linearization here. And in fact, in this case here, because the first term is 0, there's a preferred lift to the universal cover of SP2. And also because of non-degeneracy, the one is not an eigenvalue. So I have a complete thing derivative of this, which is an integer, and that's the degree where you put x in. Okay? So this is the degree. Otherwise, this complex has only a Z12 gradient at all in an even part. But in this case here, it has an even gradient. Okay? Ready? Now I'm going to prove the complete conjecture for manifold C1. Yes, question?
In the previous slide, you
Yeah.
said that this generates the cohomology. Does this happen also in characteristic P?
Well, okay.
If this would happen in characteristic P, then the proof the other thing shouldn't be too complicated.
Okay. All right. Everybody else might want to kind of stand back a little bit because it's scared. Okay. For certain classes of manifolds under certain assumptions, you can do exactly the same thing in characteristic P, and it implies the Arnold conjecture in characteristic P. And I will use those kinds of things later. For general symplectic manifolds, the proof does not work at all like this. It uses Floer cohomology with values in Morava K theories. You can forget I just said that. All right, good. Okay, now I'm going to prove the Common conjecture by contradiction. Okay? So suppose I have a field which has only finitely many periodic points. Okay? Say a periodic point of a 2 periodic point and a 3 periodic point, and that's it. So I'm going to look at phi to the 6. Okay? Then all the periodic points become fixed points. So I can just assume that there's only fixed points and no higher periodic points. Great. Okay? So because all the periodic points are fixed points, if when I do the Floer complex for any iterates, the generator is always the same. They're all fixed points. But of course, the dimensions and the degrees in which I put them actually change because the commutator changes. Great. So if I make, remember what I said about iteration of commutator indices? If you make a very large iterate, the commutator index either goes to plus infinity, or it goes to minus infinity, or it stays strictly between 0 and 2n. Now, So that means for a large iterate, all the generators in this complex are either negative degrees, or 1, 2n minus 1, or very high degrees. But remember, the complex for any case, you're supposed to compute the cohomology of the manifold. The cohomology is certainly non-zero in degree 0, and it's also non-zero in degree 2n. So it's impossible not to have any generators in the complex in this degree. And that's the proof of the Condorcet conjecture, given by Zabrodsky, which is based on index integration. That's all it is. Now, it's interesting to look at the cases where it fails. Okay, so the proof fails because you cannot assign integer gradings to generators and flow. But okay, that's not really a satisfactory answer. You could say, well, what's actually going on? Right? So what the Condorcet conjecture says basically is that if you take something which used to be a representative, used to have Condorcet index 0, it was a representative of degree 0 class, and you iterate, the Condorcet index will go to minus infinity, and so that one can no longer be a representative. And because of the way iteration works, nothing else can step in. So what happens for S2 is like this. Okay, suppose I take a rotation here with a small angle. And this, so there are two fixed points. One represents the generator of degree 0, the other at the top represents the generator of degree 2. Okay? Which are the cohomology of S2. Okay? Right? Now when I iterate, the angle theta becomes larger. Okay? So at some point I pass 2 pi. Okay? Then it's true what the argument says. This thing here, once the rotation angle becomes large, can no longer be a representative of the degree 0 class. Okay? But what happens actually, this one becomes a representative of the degree 2 class, and the other one becomes a representative of the degree 0 class. So they kind of switch places using the fact that the grading is not totally defined, and so I cannot prohibit them from doing this. Okay, so nevertheless, there are other cases where we could prove the Condorcet conjecture, and for that, I need to introduce you to a whole bunch more structural flow cohomology. And at this point, you have no chance to understand what's going on in detail, but I hope that you can get sort of the overall picture. Okay? So flow cohomology comes with a bunch of operations, which makes it into what they call a topological quantum field. So the first thing I have to explain to you what the differential of the flow complex is, because that's the model for these operations. Okay? I gave you the generators, but I never only said there is some differential such that. So remember, the generators are fixed points, which you think of as constant loops here, which are critical points of the action function. And then the differential, it measures the flow lines that go from one critical point to the other critical point. So there's sort of gradient flow lines in this infinite dimensional space. So when you think, what does it mean to have a map from R into alpha in this twisted loop space? So it was the ordinary free loop space. A map from R into the ordinary free loop space is a map from a cylinder into a manifold. Right? Okay? So in this case here, they're sort of twisted maps. So basically, there's maps from R2 into a manifold, which in one direction, the t direction here, are sort of twisted periodic. Okay? And then there should be an equation for them, which makes them sort of, in some sense, gradient flow equations for the action function. And the equation is actually the Cauchy-Riemann equation. So, like an equation for a holomorphic map. It's not quite a holomorphic map. It's a holomorphic map where the complex structure on the target space here varies. So you can, because you have U n as a maximum complex subgroup, you can put almost complex structures on symplectic manifolds. Here, you need the almost complex structure to be t dependent, because otherwise the equation for homomorphicity would not be compatible with this periodicity condition. Right? So you need the complex structure to sort of be compatible with phi and shift in time by 1. So these maps aren't exactly the same as ordinary holomorphic maps. But from a PDE point of view, that's pretty much the same thing. And you look at ones that are asymptotic to a constant as s goes to infinity and to another constant as s goes to minus infinity, which makes them sort of connecting trajectories. So let's look at them like this. So I still, in spite of the fact that they're not really periodic in T, I like to draw them like this, as if they were maps from a cylinder to M. Just I put a seam on the cylinder, and remember when you cross the seam, you're supposed to apply phi. They're not quite periodic. But I think this is a good way to draw them. Okay? And so what happens is this equation here, I brought it on R2, but you can write down similar equations for more general Riemann surfaces. Okay? And so here's the so-called example here, the so-called pair of paths. This is a surface which has two cylinders as an input, and one cylinder as an output. And you can use this to make a product structure here. Whoa. And here are the really crucial typo. copies of the Floer cohomology of phi, and he goes into the Floer cohomology of phi squared. And similarly, you can take p copies, and p times the copies to the p-fold product, it goes into the Floer cohomology of the p-iterative phi. The reason why it goes is because to make it absorb Floer cohomology classes at the input, you have to put in a seam. That's a phi seam, and then when those two seams come together, they sort of combine into a phi squared seam. That's about as much as I can reasonably tell you. So this is good, right? Especially this one here is good, because we want to do iteration. And this naturally lands in the Floer cohomology of the iterator. So the next case of the commutator conjecture was sort of, this case with the symplectic form, and the first term of the first Chern class to be 0 was with the red herring. If the first Chern class is the opposite of the cohomology class of the symplectic form, the commutator conjecture is also true, there are infinitely many iterative ones. And the proof of that uses the product structure. So basically, we do the same thing as before, by contradiction. Assume there are only finitely many periodic orbits, and then you look closely at this equation for the product structure, and it turns out to be nilpotent. Which means if you take the same element of the Floer cohomology of phi many times, and you take its product, you always get 0. And then it's a contradiction because we actually know what the pair of pairs product actually does, and it is definitely not nilpotent. Okay? Well, what does it actually do? Okay? So Floer cohomology is isomorphic to ordinary cohomology, and you might think that the pair of pairs product corresponds to the ordinary cup product, but sometimes it does, but mostly it doesn't. It corresponds to something called the quantum product. Okay, so there's good news and bad news. So the good news is this is fun. Okay? So the quantum product, or small quantum product, you take the ordinary cup product and cohomology. So the ordinary cup product and cohomology can be thought of as the intersection of cycles. You have two cycles, Poincare dually, and it intersects in two cycles. Okay? So this is a non-local thing where you look at holomorphic maps from S2 to M, and these are no local contributions. It could be you have two cycles that don't intersect at all, but there's a holomorphic sphere passing, has a point on each cycle, and then you look at all other points of that sphere, that gives you the non-local contribution. In particular, this does not necessarily preserve degrees, this quantum product. Okay? So, yeah, I know it's hard to see. So, for S2, there's certainly, S2 is CP1 as a complex manifold, so there's certainly a non-constant holomorphic map from CP1 to S2, namely the identity, and you can immediately see its effect. If you take the ordinary cohomology of S2, well, you have generator degree 0, generator degree 2, and the square of the degree 2 generator is 0. And the other's not interesting, it's the identity. If you do the quantum product, the square of the degree 2 element is 1. Okay? So as I told you, degrees are not necessarily preserved. So, if you go to an algebraist and I say I have this ring KAA squared equals 0, and this ring KAA squared equals 1, I'd say, no, these are entirely different objects. Okay? But nevertheless, the unit is always a unit for the quantum product, so it's never nilpotent, which is all that we wanted to know here. Okay, that it's not a nil. It's a unit of ring, it can't possibly be. Okay. But now, so we get a sort of Dingli feeling, where I say, okay, there's this the quantum product is related to this p-fold pair of pairs product. And we see that the quantum product, for instance, for S2 is different from the classical product. Maybe that's what explains why the Cauchy conjecture is false for S2. And then you look and you see, for every manifold with a Hamiltonian torus, actually, the quantum product is actually always radically different from the classical product. So you think, okay, now I understood the point about the Cauchy conjecture. It depends on the structure of the quantum product. This is a great idea. Unfortunately, nobody has been able to make this work. Okay? So, as far as we know, there's, nobody has even been able to say, okay, exactly what should the theorem be? If something, then something else. Then the compensator projection is yes or no, depending on some structure of this quantum product. Okay, so this is sort of, a sort of low point where there seems like there's an obvious idea which is going nowhere. And then, it's trying to do, and then this spring, lots of things started happening. Okay? And the thing that came into play is a version of the quantum product, which is a fairly strange version. Okay? Steamroll operations, quantum steamroll operations. Okay? This is a lovely thing. Okay? Okay, so now, from now on, now I have to do something, which is, if I want to have steamroll operations, I need to work with coefficients of in the field of finite characteristics, say FP or something. Okay? That's what. So, what do the classical steamroll operations in topology look like? Okay? So the classical steamroll operations are operations of the cohomology of any space, and there's a whole family of such operations. The way that, let me do a slightly primitive parameterization of this. Okay? So I want to remind you of the ZP. So now I take ZP acting and K of characteristic P, the equivariant cohomology of a point, which really speaking is the cohomology of some contractible space with a free action of ZP divided by ZP. Okay? So it looks like this. It's one dimension in each degree greater or equal to 0. I like to write it like this as a polynomial generator of degree 2, T, and then there's another odd generator of degree 1, theta. And so the t's and the thetas together, they give you one class in each degree. Sorry, maybe I should ask this. Everyone still with me? Okay? And so, okay, so for instance, if you take p equals 2, which is the most familiar case, this contractible divided by 2 is just RP infinity, and that has one cohomology class in each degree. Okay, in that case, there's no point in writing here exactly as t and theta. But for odd p, that's much better. Okay? So the classical steamroll operation is like this. You take the cohomology of your space, and it gives you a class in the cohomology of the space of degree p times the original class. Okay? Well, that would be nothing. There's obviously an operation which does that. You take your class, you take the p for the product. But actually, it's the p. It's the cohomology which is equivariant with respect to the trivial z mod p function, which means it's a cohomology tensor with the equivariant cohomology of the point, which means it has all these parameters. So for every power of t and for every power of t with a theta, you get a different map. Okay? So these are all self-maps of the cohomology. And, well, the simplest one is indeed if you don't have any t or theta, you just get, it's the ordinary p-fold cup square. Okay? So, you can think of it as, okay, what is the simplest part of the steamroll operation, the one that has no equivariant parameter? That's just the p-fold cup. Or on the other hand, you can say, no, what I'm thinking is by degree, right? So the p-fold product is quite complicated because it takes this class here and it wraps into a class in a completely different degree. I want to see what's the lowest degree I can get. And the lowest degree is up to some stupid conventions, which depend on how you set it up, is essentially you get back the same x here. Okay? Up to with some high power of t that makes it have degree p times I in this whole thing here. And you get x, and then there are cohomology classes of higher degree in the manifold, and the top one, the one with the highest degree, then ends up being this one. So that's a 2-minute introduction to steamroll operations. One thing that I wanted to say is I like to put them all together in a single map, which has all the powers of t's and thetas. And that map is obviously an injective map, because part of it is just x goes to x plus higher degree stuff. That's a clearly makes it an injective map. Okay, all right. So now, the classical cup product, has this secondary part, which is the steamroll operation, which is called its symmetries. And the quantum product, sorry, if you look at this one here, this is the quantum product. This has a Z2 actually to exchange these two input points. So the quantum product also has quantum steamroll operations. The theory of quantum steamroll operations is a mess, so they're only defined under certain assumptions on the symplectic manifolds, which I will spare you now, which has to do with the question that I got earlier. But so there are quantum steamroll operations. So let's take a look. S2, pretty much the only simple case, okay? So if I take the degree 2 class, the classical steamroll operation gives you your class with the equivariant parameter t and this stupid constant by convention, which may be 1 depending on how you set up, like to set up the operations. So for p equals to 2, okay, there's the quantum steamroll always has the classical part, which is a times t. And then it also has the ordinary quantum square. So remember, a star a was quantum product was 1. Okay. So there's also this one. So the quantum steamroll operation differs from the classical steamroll operation, just like the quantum product differs from the classical product in this case. Okay. So now, what does this have to do with iteration of maps? And now it turns out, when we did this, when we thought previously, sorry, let me go back here because it's confusing. Okay. When I drew these pictures here, there's a symmetry, clear symmetry in this picture, which I actually didn't explore. You see this one here? So I can take this pair of hands and I can rotate it around by half. So that will exchange the two input parts of the operation, and it will rotate the output part by half. And I forgot to use this. Okay? So let's go back to the definition of Floer cohomology, and I use Floer cohomology for an iterate phi to the p. And here I say phi to the p because I'm going to use the same iterate as I use coefficients to the characteristic of my coefficients. So the loop space of phi, twisted loop space of phi to the p. So you can think about it like this, maps from an interval such that the starting point here is phi to the p times the endpoint. Everybody agrees with that? That's phi to the p. Or I could think about it more symmetrically. I break up my interval into p tiny pieces, and I change the map on each piece on x1 by phi, on x2 by phi squared, and so on and so on. And then the conditions become the starting point of each piece is the endpoint of the next piece with just phi applied. And the next time, again, starting point of one is the endpoint of the next one with phi applied until I get all the way around. And now you can see that there's an obvious z mod p action here, okay, where you rotate these p components around. Everybody sees that? So the loop space of the iterate comes with this z mod p action. Here I tried to draw this z mod p action, 3 plus 3. I'm not sure being successful. And it's compatible with the p-full pair of pans product, meaning you can apply the z mod p action here, and it will correspond to rotating these things here, these p tensor powers at the input cyclically. Okay? Is anybody a topologist here? Probably asked me when I defined steamroll operation why I'm using the cyclic group and not the symmetric group. So the quantum version only has cyclic group symmetry. This kind of symmetric group it does not exist in the quantum version. So, so I get a sort of an equivariant counterpart of this pair of pans map, which is a random Floer cohomology. It starts from a Floer cohomology of phi, and it goes to the Floer cohomology of phi to the p. And it's a p power map, but it goes into a sort of ZP equivariant version. This ZP equivariant version is isomorphic to the ordinary cohomology coefficients with the ZP equivariant coefficient rate. And this p power map is, it's actually isomorphic to this quantum zero operation. In the same sense as the ordinary pair of pans product was isomorphic to the quantum product. Now we have some traction. Okay, this is a horrible sentence. Let me read it out to you so you can see how horrible it is. Okay? So unlike the ordinary pair of pans product, the equivariant version knows that a fixed point is also a periodic point. Well, what the hell does that mean? Okay? So this means that when you write down what's going on here on the level of chain complexes, there's always a non-zero local contribution where you take p copies of the generator that's a fixed point, and you get the generator that's a periodic point. And weirdly enough, that was not the case for the ordinary pair. For the ordinary pair of pans product, that contribution is 0. So there's some local geometric information here where it remembers that if you have a fixed point, the same thing will be a periodic point. Okay? Which clearly, if you want the Condic conjecture, that is sort of the key aspect. And indeed. Okay? So now I have to break it down for you into two parts. So nowadays, so many people think of approaches to the Condic conjecture into two parts. And so one part is to look at maps which have the least possible periodic points that you could possibly have. So the number of fixed points is the rank of the cohomology. And so that I don't have to say which coefficient field is used, let me assume that the cohomology is total. Okay? That's the lowest number of fixed points that the Arnold conjecture allows. And we assume that there are no other periodic points whatsoever. Okay? So, oopsie, sorry. There you go. So, so this means that so this chain complex here, because it computes the cohomology, that it has as many generators as the cohomology, the differential is always 0. And also because there are no periodic points, the complex of phi for all iterates is actually kind of, well, as a vector space, it's the same, with gradient differentials. So these are called, these things, which are like the rotation of S2, the irrational rotation of S2, they're called quasi-rotation or pseudo-rotations. Well, I call them quasi-rotations and pseudo-rotations. To be honest, both are controllable. Okay? Okay, so one approach to the Conley conjecture is to look at this extreme case, where you not just have finitely many floating points, but as few as you can possibly get away with, and then look at the other case separately. Okay? So the idea is that in many cases you can prove that if there's one more periodic points, you must have infinitely many. So we look, so that leaves this case here. This case of pseudo rotations. Okay. And so here we start. Okay, so in May this year, Shulukin proved this thing, and it's usually the first theorem in some direction comes with a bunch of assumptions. Okay. C1 is equal, the first term is equal to the cohomology plus the symplectic part. You could probably weaken this a lot, but never mind, because this is part of the interesting case. Then assumption 3, the first Chern class is divisible by some integer which is greater than half of the dimension of the manifold. A horrible thing which is satisfied with the projector state, but almost never. But never mind. And you assume that the quantum steamroll in there is equal to the ordinary steamroll, okay? Which fails for S2. Then there are no pseudo rotations. Okay? So from this point of view, the reason why S2 has pseudo rotations is that the quantum steamroll product is different from the classical steamroll. And so then a couple of months later, two groups separately, Seidel and well, they had been working on this at the same time as Shulukin. And then Shulukin himself, they actually dropped this assumption of the divisibility of the first Chern class. So this will be sort of consigned to the heap of history, this class here. But because these are so recent, so priorities will count, so I wanted to be a good boy. Okay? So, okay, so now we have some clue. Okay, we could say the Conley conjecture fails if the quantum steamroll product operations differ from their classical thing, but differ by exactly how much, to be honest. Because there are some manifolds where certainly the quantum steamroll is different from the ordinary steamroll, but the Conley conjecture is still true. So we haven't, where is the boundary we're moving? Okay? So, as this is my next slide, is my last slide, gradually. So let me give you a possible direction here, which I don't know. This is like changes, and it seems like change every month or so. So you remember when I said the steamroll operation, ordinary steamroll operations, is injective as a total map. Okay? So I'm going to say, okay, let's look at the quantum steamroll operation. And again, this is a map which we have these p's and theta parameters, but I'm going to divide by some power of t. Okay? And I'm going to take the largest power such that this is not, so if I divide by higher powers of t, I get more space in here. So, eventually this map becomes injective, and I'm asking when does it become injective. So I'm going to introduce an integer L depends on prime p, and it says, okay, this is the largest integer, it's not injective. Just as a classical, let's say the classical steamroll operation. If I take the top cohomology class, the Poincare rule of a point, okay, the only thing that happens is you get back to the Poincare rule of a point with a fairly high power of t. So if you divide out by this power of t or anything less, it will not be injective. So roughly speaking, the power at which it's also injective is n times p. It's an order of magnitude, n times p. Okay. And n times p minus 1. So I say, okay, so if it emits a pseudo rotation, and you take this LP and you divide by p, so in the classical situation you get n as a limit. But if it emits a pseudo rotation, and this one here is less than n. Actually, in fact, for S2 it's actually 0. So this is just by, it's unpublished, it's just an idea of saying, what is it about the quantum steamroll operations that actually makes these pseudo rotations appear? Because just saying they're different from the classical ones cannot actually be the right thing. But whether this is the right thing or something else is the right thing, nobody knows. The end. Okay? Now, one more thing I want to say. So what's going to happen on Monday and Tuesday? Because you're all wondering, gosh, if this is the continuation, I'm never going to show up on Monday. Okay, good. So those are not actually, it will help on Monday, Tuesday if you've been here, but they're not actually continuations. So on Monday, so what turns out here, you saw that I used flow homology with coefficients of mod p, and that was sort of interesting. So the question is there anything more than? So on Monday, I'm going to look at sort of arithmetic aspects. Right? So is there an arithmetic geometry behind this use of mod p coefficients? And what's really helpful is that we can sort of bypass, instead of building the whole machinery and then asking the question, there is mirror symmetry, which translates the whole thing into algebraic geometry. So we can ask, if we're thinking in terms of algebraic geometry over a field of characteristic P, what are we actually looking at here? And in case you don't know anything about algebraic geometry and characteristic P, I also know nothing about algebraic geometry and characteristic P. So we'll be on the same level. Okay? So I will continue this in an arithmetic direction, and on Tuesday, I will tackle, we have Floer cohomology. So the question is, do we have, Floer, K-theory, cobordism, Floer, stable, homotopy? Okay, this is a scary question, but there are a lot of younger guys who are very comfortable with peepering away at it. So I'll try to give you a sort of introduction into this kind of homotopical thinking, but using a completely different kind of question in symplectic topology as a motivation.
Can I formulate what would you say that there is some condition under which we still have kind of correct notion number of fixed points? Or you say you can measure the failure to have an expected number of fixed points. What is it?
Okay, so there are. So for most symplectic manifolds, you need to have infinitely many periodic points. Okay? The question is, what characterizes the class of manifolds for which this fails? Okay? Let's say the ones for which it is possible, even though very untypical, possible to have only the minimal number. Okay? And this is one of my attempts to do it. Okay? And this is their attempt to do it. Is this condition here? Okay? Or let's say ours, because I just told you. And all I wanted to say to you is nobody really knows. We think now, we know that the word quantum steamroll operation has to be somewhere in this condition, okay, since this May. But exactly what the sentence is that it's in, we do not know yet. Yes?
Maybe you answer, but didn't understand. So how did the steamroll operation how did it rise? Why should you thought about it?
That would be a question for Shalukin. No, I think that I cannot do this without kind of praising myself, which is kind of embarrassing. So I wrote a paper a couple of years ago about this equivariant product, where I pointed out this one here. And I thought this would be useful for iteration, but I could not actually make the argument, which is extremely simple. It takes only a page, work, which produces this kind of results here. So somebody woke up and said, oh my God, I don't want to do this.
We were talking about the Lefschetz fixed point theorem and being a motivation for the determinant of 1 minus.
No, this is the determinant of 1 minus this is the sign with which the fixed point contributes to the Lefschetz fixed point number. Right? So the Lefschetz fixed point formula says if you have a map phi that's isotopic to the identity, you count fixed points with this plus or minus 1 sign, then you get the Euler characteristic of the manifold. Which if you take everything that I said, so Floer cohomology plus the Euler characteristics, you recover Lefschetz fixed point.